Welcome back to Probability and Statistics. This is Lesson 5. We are in Chapter 7 from Elementary Statistics, 4th edition by William Navidi. In this lesson, in Chapter 7, we are going to look at what's called the normal distribution. We'll start by just talking about distributions in general, what are called density curves, and then kind of use that to get into specifically this idea of a normal distribution. This is kind of a big topic in an introductory course like this, where we are looking at uh, in the normal distribution. We're going to be seeing this used a lot as we move forward in the remaining lessons that we have. So obviously we'll talk about what is a standard normal curve. We'll talk about kind of the characteristics. We'll talk about how to use it, look at some examples of how to find area under that curve, and then we'll get into what's called the central limit theorem, which is kind of, I guess, a guiding principle of when it's appropriate or not appropriate to use a normal distribution in describing a data set. So with that, let's go ahead and get going here. So again, we're going to start by just kind of generally talking about what's called a density curve. So a density curve, if you think about taking data and putting it into a dot plot or a histogram or some visual representation like that, where you can see the shape of the data. So maybe I have a histogram that looks like, like something, I don't know, something like this, right? And I can kind of think of the shape of that data. I can kind of fit a curve over that data. It's that curve that we want to talk about now in this lesson, and that's what we call a density curve. So a density curve represents the probability distribution for a continuous variable. So that curve is basically giving us, is representing all of the data in our set. And it's a way to think about that data from a standpoint of probability and proportion. The area under the curve is always 1. And that is just because, again, we've got all of our data. It's 100% of our data. So we think of that area being 1 or 100% of our data. And as I mentioned in the introduction, one of the things that we can do then is we can start to think about, well, how do you find area, excuse me, between two values A and B? Or maybe I want to find the area strictly to the left of A or to the right of B or something like that. When we do that, though, so let's say I pick two values A and B, and I want to find the area between those two values. The area that I find can be thought of in one of two ways, or really in both of these ways. One is that it's the proportion of all of the data within that range. So let's just suppose, for example, that this area is 0.35. That means that 35% of all of the data is between those two values. But that also means then that if I was to randomly select one value from all of the values in that set, there's a 35% probability that that value would come from that shaded region, because that's the proportion of data that covers. So that's a density curve. And density curves can come in all sorts of shapes and sizes. We've talked about, for example, data sets that are skewed left, skewed right, symmetric, uniform, all of that. And those are all examples of density curves when we think of them as curves representing the overall shape of those sets. So one in particular that I want to talk about briefly before we get into the normal curve is the uniform distribution. And the uniform distribution, again, if you think of the name, uniform means kind of the same, right, or consistent. So in this case, it's a situation where we'd expect all of the outcomes to be equally likely. Now, in this case, we do often think of this more than in terms of discrete variables, things like rolling a die, where you have a 6-sided die. All 6 sides are equally likely to show up on a roll. And therefore, if I think about doing this many times, my overall distribution would start to look like a rectangle, where this is 1, 2, 3, and so on. And the heights of each of these would all be the same. Okay. Now I'm going to get rid of that for the moment because I want to talk more generically here. So let's suppose that this uniform distribution had a width of k. It went from 0 to some value k. Now keep in mind that the area, because it is a density curve, the area is 1. So the height then of this rectangle would have to be 1 over k, because we know that area of a rectangle is length times width, or in this case, you can think of it as base and height. And so if I take k times 1 over k, that would give me an area of 1. So when you're dealing with a uniform distribution, you often will know the width because the width is just the range of the values that you have. You might be dealing with values from 100 to 200. Your range is 100. That's the width of your rectangle. The height then has to be 1 over 100. And why that's important is because now if I want to find the area of a sliver of this, let's say I want to find that area, and I know that this width, for example, is 5, and let's just for argument's sake, let's say the height is 1/10. I could take 5. Well, that wouldn't make sense because it'd be a lot more than that. Let's make this 1 over 40 or something like that. Okay, so maybe the whole width, maybe k is 40, so the whole width of this rectangle is 40. The height is 1 over 40. If I want to find the area of that shaded region, I can just take the width of 5 times the height of 1 over 40, and I get 5 out of 40, or 1/8, or as a decimal, 0.125. So 12.5% of the data would be between those two points. Okay, so let's talk now about the normal distribution. Again, this is what the lesson really focuses on, is the idea of this. So a normal distribution is a symmetric curve that is bell-shaped. So might look something like this. And I'm not real good at drawing this shape, but that's basically what it is. So normal curve is symmetric, it's bell-shaped. So symmetric, bell-shaped, or bell curve. If you want to just think of it as a bell curve. One of the characteristics of this is that oftentimes we think of the ends as extending indefinitely. So ends extend indefinitely. And the reason that that's important is because when you think about data, yes, there are definitely times where we would know a minimum and a maximum value that are possible for that data set. So consider, for example, test scores. A test might be given where students can score between 0 and 40 points. Obviously, you can't get below 0, and if the max is 40, you're not going to get above 40. So you would know that the ends would be 0 to 40. But a lot of times that isn't the case. A lot of times in data sets, in real life situations, yes, there is a typical range of values that we would expect, but there's always that possibility for an outlier. There's always that possibility for that really large number that's far away to the right from the data, or that really small number that's far to the left of the data. And so we think of these as just extending indefinitely to allow for that idea of those outliers. Because it is symmetric, we would have a mean directly in the center, and the mean would also be equal to the median. The median would be in the same place if it's truly symmetric. And then finally, it follows what's called the empirical rule. So follows empirical rule. And obviously I'll explain what that is, and we'll show that in the diagram. But the empirical rule is really just a way to quickly approximate either where a value is in relation to the mean and other values, or to also figure out very quickly the proportion between two values. And so what the empirical rule says, and again, this is only for a normal distribution, this would not be true for anything else. If I have my distribution, I'm going to mark out 1, 2, and 3 standard deviations from the mean on both sides. So this is 1 standard deviation, this is 2 standard deviations, this is 3 standard deviations, and then going the other direction, same thing. If I want to think about what percent of data in a normal distribution is 1 standard deviation from the mean on either side. So thinking about this kind of the center region, -1 to 1 standard deviation, that whole area is about 68% of all the data in a normal distribution. Now, these are not exact values. These are approximations, but it's about 68%, or if you want to think about it, about 2/3 of your data would be within 1 standard deviation of the mean, or from the mean. Going 2 standard deviations out, you would have about 95% of your data, which is most of it, right? You've got only 5% remaining for those ends. About 95% is within 2 standard deviations from the mean. And then 3 standard deviations, you're talking about almost all of your data, 99.7%. So you will sometimes see it just called the 68, 95, 99.7 rule, because those are the percentages. And again, what this does is it just gives a way to quickly estimate, if you're dealing with values that are right on those standard deviation values, and we'll do an example in just a minute of this, to estimate about how much or what percent of data you have in that range of values. Okay, so with that, let's go ahead and do that. Let's take a look at an example. And we are going to look at the weight of adult dolphins. It says that the weight follows a normal distribution with a mean of 400 pounds and a standard deviation of 20 pounds. Sketch the curve labeling the weights at the mean and the 3 standard deviations on each side of the mean. And then we're going to use that to find the proportion of dolphins that weigh between 380 and 440 pounds. Okay, so let's go ahead. I'm going to make a nice big graph here so we've got room to write everything and really see these percentages and areas well. So when we label a normal curve, we want to just use an n for normal and then state what the mean and the standard deviation are. You don't need to actually put the mean and standard deviation symbols. I am just doing that for your own reference. So we would just write n and then in parentheses 400 comma 20. That's how we label a normal standard or a normal distribution. Okay, we've got a mean in the center at 400. And then we are to draw out 3 standard deviations to either side. So basically, because the standard deviation is 20, we'll just add 20 for every tick mark to the right. We'll subtract 20 for every tick mark to the left. And so this is 420, 440, 460. And this would be 380, 360, and 340. Okay. Now, just as a quick reminder here. So again, 1 standard deviation away on either side, that's about 68% of our data. 2 standard deviations away, that's about 95% of our data. And 3 standard deviations away, that's about 99.7% of our data. Okay. So for example, then, we would anticipate or expect that about 68% of adult dolphins weigh between 380 and 420 pounds. We'd expect 95% of adult dolphins, to weigh between 360 and 440 pounds, and 99.7%, or almost all dolphins, to be between 340 and 460 pounds. And again, so as we think about this, we can think about, extreme values, right? So if I'm a dolphin, which would, I guess, kind of be cool, but if I'm a dolphin and I weigh 470 pounds, I'm a pretty heavy dolphin, right? I'm a rare dolphin in that regard because there's only 0.3% in total on both ends, which means there's only 0.15% on the left and 0.15% on the right beyond 3 standard deviations. So I'm in a class of about 15 hundredths of a percent of dolphins that would weigh more than 460 pounds, right? And so that's kind of one way we can think about this data. The other is then obviously just think more holistically. So in this case, we want to know, for example, what percentage of dolphins would we expect to be between 380 and 440 pounds? So we're basically looking for this area right here. Well, we know that basically from here to here, that's that 68%, right? That's that. And then this part right here is part of that 95%. Now, there's different ways that we can do this. The way that I'm going to do it is I'm going to take 95 minus 68. Oops, 95 minus 68, not 98. I did it again. 95 minus 68 is 27. So that means that this region over here and then its counterpart over here in combination would be 27%. So this half or this part would be 13.5%, and this part would be 13.5%. So you can start to break this down into smaller chunks. And in this case, then I'm concerned about the 68%. I'm concerned about this 13.5. that gives me the total area. So 68 plus 13.5 is going to be 81.5, or in this case, 81.5%. Or as a proportion, you could just leave it as 0.815. So about 81.5% of dolphins would be between 380 and 440 pounds, at least according to this model. All right, so that's how we kind of do that and can use that. But what happens if you aren't right on a standard deviation? What if I want to know the percentage of dolphins that are between 362 pounds and 398 pounds? Well, this is not going to be very helpful for me. And so that gets into what's called the z-score. So let's talk about that. We're going to get into now finding area really for any values under that curve. So z-score is a way that we basically take the values and we do what's called standardizing those values so that we can then find the area. So z-score, I'll give you the formula and we'll talk a little bit more about this. Z-score is value minus mean divided by standard deviation. Okay, so what we're doing again is we're taking a value from a data set, we're going to subtract the mean, and we are going to divide by the standard deviation. What this does is it creates a value, z, that tells us how many standard deviations above or below the mean we are. So z is the number of standard deviations above or below the mean. When we do this formula, we want to make sure that we do value minus mean in that order every time. If you get a positive value, you're above the mean. If you get a negative value, you're below the mean. Okay, so this would be a positive value. This would be a negative value. And then the other thing that I mentioned is that it standardizes data values to values in a set with mean equal to 0, and standard deviation equal to 1. Okay. I won't get into all the mathematics, but if you just kind of think really quickly about this, if I take all the values of a data set, maybe it's a data set, we'll take our dolphins, for example, a mean of 400. So I'm going to subtract 400 from all the values. That means my mean reduces by 400 or now becomes 0. Then I'm going to take all of those values and divide by the standard deviation. Well, when you divide by the standard deviation, in this case 20, that takes that standard deviation and crunches it down, reduces it down to 1. So that's really all we're doing when we find the z-scores. We're just taking all the values and creating this data set, this new data set that would have a mean of 0 and a standard deviation of 1. More importantly, it tells us how many standard deviations from the mean we are. One of the reasons that this is important, we'll see this example a little bit later, is if I want to compare values that maybe aren't directly comparable to each other. So for example, if I give a test to some students and they all take the same test, I can clearly tell who does better than the other simply by looking at their scores. A 95 is going to be better than an 88. But let's suppose I give a standardized test like a reading test. And I give a reading test to third graders, and then 3 years later, I give it to them again as sixth graders. Well, now that score we'd expect to be higher as a sixth grader, but I'm not just concerned about the higher score because, again, that's expected. What I'm more concerned about is how is that student doing compared to their other classmates in third grade versus sixth grade. For example, let's say a student is, one standard deviation above their classmates in third grade, but now in sixth grade is a half standard deviation below their classmates, right? The score itself might actually be higher from third grade to sixth grade, but when I reduce it down to a z-score to standard deviations, I find that student is falling behind their classmates. So that's a way we can use z-score also to compare in situations where you want to see that change, that difference, but it's not a direct comparison of values, and you have to use something like this to do that. And like I said, we'll see an example of that in just a little bit. All right, let's go ahead then and let's take a look at how do we find then z in an actual application, and then we're going to use that to step into finding area under the curve. All right, so it says the scores for a recent 100-point test follow a normal distribution with the mean of 85 and a standard deviation of 10. Find and interpret the z-score for a test score of 91 and for a test score of 72. All right, so very simply, to find z, again, we take the value minus the mean divided by standard deviation. So the value is 91. That's the test score that's in consideration here, minus the mean of 85 divided by the standard deviation of 10. And that gives us 0.6, which means that a score of 90 or 91, score of 91 is 6/10 of a standard deviation above the mean of 85. Okay. And then likewise for the score of 72, if we take 72 divided by 85 divided by 10, that gives us a z-score of negative 1.3. So a score of 72 is 1.3 standard deviations below the mean. So notice that I dropped the negative because we don't really need the negative if we're describing where it is. But that negative just tells me that we are below the mean. So that's how we find z. Pretty straightforward. Now what do we do with that? So let's talk about area under the curve. Now, like I said, one thing we can do with z that we'll see later is using it to compare results on a test score. But the other thing we can do is use it to help us find area under the curve. So if we want to know that kind of that proportion or probability of data that falls within a certain range, this is how we do that. Now, why z is important is honestly not quite as relevant today as it was, let's say, 40 years ago. Because now with technology, you can use things like graphing calculators, Excel, Google Sheets, actual statistical software, where you just literally put in your data and it could give you all this information, or you just need to throw in some other stuff. You wouldn't need z to find the area under a curve. 40 years ago, we didn't have that technology. And so we would have had to use tables to look up these areas. And that's actually still sometimes used today. And so we're going to actually use a table. I'm going to show you how that works and why z is important in that context. But understanding also that if you have technology and you're comfortable using that technology, use the technology. When we're done with this, I will explain or just quickly show how you would do this on something like Excel or Google Sheets. Okay, so we are going to find the area under the curve, and we've got three different scenarios. We're going to look at to the left of a value, to the right of a value, and between two values. And this is important because how even if you are using something like Excel, you have to be very aware of the numbers that it's going to give you as answers, because they're not always the numbers you're actually looking for. Okay, we'll explain that later. All right, so we want to find area under a curve to the left of negative 1.3. So I always like to draw a picture just to help kind of see what's happening here. It also helps to make sure that when I get my answer, it makes sense. So we have, we're given z-scores, which means, again, that the mean is 0, the standard deviation is 1. So I'm just going to label my graph like this. And so here's 0, the mean. We have a z-score of negative 1.3. And we want the area to the left of the curve. So we want to know what proportion of data is in this region. First thing we would need to do if we didn't already have it is find the z-score. We already have it, so now we can go to the next step of actually finding the area. Like I said, we're going to use a table to do this at first, and then I'll show how to do this in Excel. So if we're going to use a table, you obviously need a table, and what you would be looking for is something that looks like this. This is called a standard normal probabilities table. If you just look up standard normal table, you will find all sorts of examples and PDFs of tables like this. But what you're looking for is something that is giving you, the input's a z score, and then the body of the table is outputting the area under the curve. Specifically, if you look at the graph at the top, it's giving us the area to the right of that z-score. Or excuse me, to the left. Sorry, to the left. My other right. Okay, so we're going to the left of z. And that's important because, again, right now, that is what we're trying to find. We're trying to find the area to the left of negative 1.3. But when we go to the right, we have to do something a little different here. Okay, so to the left, what I'm doing is z actually goes down the left column, but it also goes across the top row, because what that does is, in combination, it gives you a z-score to 2 decimal places. So the left column, negative 3.4, negative 3.3, negative 3.2, and so on, is giving you the whole number and 1 decimal place. And then across the top, it's giving you the second decimal place, 0, 1, 2, 3, and so on. So in our case, where we want a z-score of negative 1.3, right, we're looking up z equals negative 1.30. I'm going to go down to negative 1.3, which is here, and then 0, which is the first column. So this is my value. And that is our answer. We're looking for the area to the left. That is the area to the left of negative 1.3, which is 0.0968. Okay. Before I go back up to the problem, let me just kind of quickly show you this. This particular table, and a lot of tables that you find will likely be like this. This has 2 pages to it. The first page has all negative z values, so all of your values that would be to the left of the mean. And then the next page has all of your positive values, which are all of the values to the right of the mean. But notice that in both cases, you are always finding the area to the left. Okay. All right, so our answer was 0.0968. Let me go back up to the problem and write that in. So here we have an area of 0.0968, or about 9.68% of our data would be below negative 1.3, whatever that corresponds to as a test score or a weight or whatever it might be. Okay, now let's go to the right. So in this case, we are going to the right of 0.6. So again, labeling our graph. Here's 0, here's 0.6. And this time we want to go the other direction. We want to go to the right. Same table, same process, one additional step that we're going to have to do here. So let's go down to the table again. And we are looking for a positive 0.6, which is right here, again, ending in 0.60. So we're going right to that first number. Now, that number is 0.7257. I'm going to go back up top and let's talk about, up to the problem, and let's talk about what that is, 0.7257. So remember, that table always gives us values to the left. That value is all of this. This is 0.7257. Okay. Now, the reason I like pictures is because in this case, for example, I can look at the picture and go, wait a minute, that number wouldn't even make sense. I'm looking for a value that's clearly less than 50%, less than 0.5, because I'm shading in less than half of the graph. The reason that that's not correct is, again, because it's to the left and not to the right. Well, remember, the area under the curve is 1. So if I subtract what I don't want from 1, I will get what I do want. So to find the area, we are going to take 1 minus 0.7257, and that gives us the actual area to the right that we're looking for, which is 0.2743. That's our area to the right, 27.43%, which, again, looking at our picture, makes a lot more sense. Okay, last one is to find the area between 2 points, and we're going to change up the numbers here just so we can get a little practice with something other than that first column. So here's 0. We've got negative 0.32 and a positive 1.15, and we are looking for the area now between those two. All right, let's go to the table. Let's find those values. And so again, looking up negative 0.32. And so negative 0.32, well, here's negative 0.3. This would be 0, 1, and here's 2. So that's the value that we're looking for on the one hand, 0.3745. And then since I'm in the table, I'm going to go right to finding the other one, the 1.15. And so going to the positive part, here's 1.1. Here's 0, 1, 2, 3, 4. And obviously you can see up in top, we're going down this column, and there's the value for the other one, 0.8749. Okay, let's go back to the problem. Let's talk about how to use these values now to find that area between. So again, keeping in mind that what we just found was area to the left of those values. So the area to the left of 0.32 was 0.3745. And the area to the left of 1.15 was 0.8749. So if I was just finding area to the left of 1.15, right, it's the 0.8743, but I don't want this part. I just want this part. Well, this part right here is this number, right? This represents that unshaded region. So if I take the entire region to the left of 1.15 and I subtract the 0.3754, I will get the area that I'm looking for. So when you're finding between, just find your two numbers in the table and subtract them. So in this case, that gives us an area of 0.5004. So pretty much 50% of our data we would expect to be between the two values that we have here, negative 0.32 and 1.15. Okay, let's go ahead and do one more example here, finding area between the curves. And as I will often say, I would encourage you to stop the video, try it on your own, and that's just a good opportunity to see where you're at in terms of your own understanding, and then start up the video to watch the solution play out. So for this one, we are finding area under the curve between negative 1.33 and 0.76. So N01, here's 0, negative 1.33, and 0.76. All right, so we're finding that area between. So I'm not going to jump down to the chart. Hopefully by now you are comfortable finding those values. But basically 0.76 in the chart, you should find 0.7764. And then for negative 1.33, you should find a value of 0.0918. And again, we just subtract those to get our area. So our area is 0.7764, minus 0.0918, and that gives us 0.681. Okay, before we jump into the last examples that kind of relate to this, let me just talk quickly about Excel. Google Sheets, again, would be the same notation. But if you want to use Excel or Google Sheets to do this, what you are going to do is just type in equals norm dot dist, so norm dot dist for normal distribution. And then what it's asking you to find or enter is x, mu, sigma, and 1. So you're plugging in the value, the mean, and the standard deviation. So think about the fact that those are the three values that we need to find the z-score. So you're giving it those three values, and it's going to use that to do exactly that. It's going to find the z-score and then just convert that z-score into an area. Okay. Now, like the chart, this also will only give you area to the left. So when you do this, you want to make sure that if when you get that answer, it's basically just digitizing the chart is all it's really doing. It's just going to do the chart behind the scenes and give you that value to the left. So you still need to do the 1 minus if it's to the right. You still need to subtract the two values if you're finding between. If you're using something like a graphing calculator or certain statistical software programs, a lot of times those will allow you to specify that you are finding to the right or between, in which case then it would give you the value immediately. It would give you your answer right away. All right, so that's how you do that in Excel or in Google Sheets. The other thing I will just mention very, very briefly about that is you might get a slightly different answer using technology than you would in the chart, and that is perfectly okay. One of the things that often happens is because charts are rounded and technology can do a much better job of being precise. That will happen from time to time. And that's perfectly acceptable in statistics. Keep in mind that everything we do in statistics is already an estimate, because when we're doing this, remember, we're doing this under the assumption that our data is symmetric and fits a bell-shaped curve, and a specific bell-shaped curve with that 68%, 95%, and so on. Well, most data isn't going to be that, right? Most data is going to be off a little bit. It's not perfectly symmetrical. It's not perfectly bell-shaped. It's not exactly 68% of our data between -1 and 1. So we're already making estimates and approximations. So to be a little bit more off due to using a table versus a technology, perfectly acceptable. Okay, let's go to our last examples on this idea specifically, and then we'll get into some other stuff here. So notice here now it says find the z-score that has an area of 0.37 to its left, and then find the z-score that had an area of 0.16 to its right. So it's flipping this around now for us. So now when we think about our charts, let me go back to blue here. When we think about our picture, I should say, we don't have the z-score, we have the actual area. So 0.37 to the left, so here's 0, 0.37, so we're looking at about 37% of the area to the left. And this is what we want to find. We actually want to find the z-score here, right? Knowing that the area here is 0.37. So this is just a simple matter of just kind of working backward in the chart. And so in this case, if we go to the chart, I'm looking at the body for 0.37 and then just cross-referencing the z-score for that. So in this case, I'm looking at the chart. I'm just looking for the number closest to 0.37, which looks like it's going to be maybe about right. Well, here's that's 0.0, not 0.37. Sorry. Let me try that again. I got to go up, down further. 0.37 is going to be somewhere right around, maybe about right here, right? We're looking at kind of those values. This one would definitely be the closer value, though, right? That's 7 thousandths away. The other one is 31 thousandths away. So that is negative 0.3. And then if we go up to another 3, so it's negative 0.33. So that's our z-score for that problem. So this is going to be, find that problem again. This is going to have a z-score of negative 0.33. Okay. All right, so now it says find the z-score that has an area of 0.16 to the right. Okay, so now here's 0. We're looking for just kind of this area right here, and we want that that variable, or that value, I should say. Area is 0.16. Okay, now again, we have to be careful here because that chart is to the left, not to the right. So what I want to do here, and there's two ways to do it. I would just say find the area to the left. So if it's 0.16 to one side, 1 minus that is 0.84. So it's 0.84 to the left. So instead of looking up 0.16 in the table, let's just look up 0.84 in the table. So going down to the table, 0.84 is going to be on the positive side of the charts, and 0.84 looks to be, let's see, we've got a 0.8413 here, and then at the end of the row above it, there's a 0.8389. Technically, in this case, then the 0.8389 is closer, right? That's 11 thousandths away versus 13 thousandths away. Now, again, one or the other, they're both giving us roughly the same information. But to be technical about this, we'd want the 0.99 versus the 1.0. So 0.99 is our z-score for that problem. All right. Here we go. Okay, so that is 0.99. All right, so just as a reminder, again, here's the formula. Z, value minus the mean, over the standard deviation. And Z is, again, number of standard deviations above if it's positive or below if it's negative, the mean, okay? All right, so let's move on here a little bit. And I guess we'll do one more example, and then we'll move on. Sorry about that. So it says a bag of M&Ms has on average 56 candies with a standard deviation of 2.6. What is the probability that a bag has more than 60 candies? Okay, so it's really exactly what we're just doing. We're just creating that context now, that idea of probability with what we've been doing. Okay, so but it's the same thing. We are going to take our curve. In this case, we have a mean of 56, standard deviation of 2.6. So here's 56. And this time, we want to, so basically, it's what is the probability that a bag has more than 60 candies, okay? So these numbers in this data set would represent how many candies are in a bag. So on average, 56 candies in a bag, 60 or more is what we're looking for. So when we find that value, that's going to be the probability. So in this case, we don't have a z-score. So we have to start by finding z first. So value of 60 minus the mean of 56 divided by the standard deviation of 2.6. That gives us 1.54 for the z-score. And then again, look, going to the table, and I'm not going to go down to the table and show you this, but if we went to the table, we would find that the area is 0.9382. But again, that's not what we want, right? That's to the left. We want to the right. So the probability that x is greater than or equal to 60 is 1 minus that value, or 0.06818. So there's about a 6.18% probability that if I just randomly draw a bag of M&Ms, that it would have 60 or more, that it would have more than 60 candies in it. Okay. One thing I should mention is with these curves, because they are they're technically working with continuous here. This one strictly says more, and I guess I actually wrote more than or equal to here. In this context, you're going to get the same answer. You can't differentiate between greater than, or equal and greater than. They're both going to mean the same thing in these types of problems. Okay, let's move on now. Let's start to get into this idea of central limit. This is kind of the second big theme of this lesson. And so we're going to start by just looking at an example and think about how central limit, this idea of what the central limit theorem is that we'll learn later, plays into when it's appropriate or not appropriate to use a normal distribution. So it says, consider a four-sided die with faces 1, 2, 3, and 4. And so imagine rolling that die and rolling it 3 times and taking the average of those 3 rolls, okay? And then finding the standard deviation. Now, what you see below is the sampling distribution for that. So rolling the die 3 times, you get a 1, 1, 1, a 1, 1, 2, and so on. So these are all of the possible outcomes of that. And then you've got this column, which is the mean or average of those 3 rolls, okay? So this mean right here is really kind of the average of the averages. It's the average of those means. And the average of those 3 rolls would be 2.5. The standard deviation is 1.118. Now, you would not find these by hand. You would use technology to do that, and that's what I did. I put this into an Excel sheet and basically had Excel find the mean and standard deviation for me, okay? But the idea is this, that When I think about the average of those averages, okay, so think about sampling now. When I sample, um, I roll a die 3 times and I do it, maybe 50 times. Every time I do that, I get a different sample, and therefore I get a different sample mean and I get a different sample standard deviation. We've talked about this idea a little bit before, okay? Um, when I think about then the mean of a sample, I would expect, though, on average, that the mean of that sample would still be 2.5, right? I would expect that if I take a sample of 50, roll a die 3 times and do that 50 times, take the average of the 3 rolls, take the average of those averages, I would still expect it to be about 2.5, all right? If I wanted to find the standard deviation for the samples, right? So standard deviation for the population is 1.118. When I want to find the standard deviation for the sample, what I would do is I would take the standard deviation divided by the square root of n. All right. So in this case, if I'm going to do this 50 times, I would take 1.118 divided by the square root of 50, and that would give me this standard deviation of the sample. All right. Also sometimes called standard error. Sometimes when we're dealing with the sample, you will hear this called standard error. Okay. All right. So let's kind of then talk about why. Let's go through an example and see how this is applied, and then we'll get into the why and what this means. So let's say we've got the mean height of adult women in the United States is 65.5 inches with a standard deviation of 2.5. We're going to find the mean of the sample and the standard deviation for the sample with a sample size of 50. Okay. So again, the mean of my sample, I will always expect to be the same as the mean of the population, or in this case, 65.5 inches. My standard deviation for the sample that I would expect to get if I'm doing this, taking a sample size of 50, is again the sample or the standard deviation for the population divided by the square root of n, which in this case would be 2.5 divided by the square root of 50, which is 0.35. Okay. Now, here's the issue, and here's where we start to get into this idea of central limit theorem. Thinking about this standard deviation in particular, and even the mean for that matter, if I take a very, very small sample, this probably isn't going to play out this way. If I sample 2 women in the United States and I take the average of their heights and the standard deviation of their heights, I'm probably not going to get 65.5 and 0.35 or anything near those, okay? And so I'm going to get a very, very wide variety of sample means and sample standard deviations as I'm taking samples of size 2. Even samples of 5, I'm probably going to see a lot of variation. But as my sample size gets larger and larger, I would expect the values, these means and standard deviations, to get closer and closer to the values that we calculated here, right? And ultimately then, if I get large enough, I'm going to expect my standard deviation to actually get closer and closer to the 2.5, okay? So the idea is that when we're using normal distributions, when we're thinking about the formulas and values that we're finding from that, we have to really be conscious of our sample sizes in terms of whether or not that sample size is large enough to produce the results that we would expect. So the central limit theorem basically says that. It says let x bar, so the sample mean, right? So this is the mean of a simple random sample, the mean of a simple random sample from a population with mean equal to mu and standard deviation equal to sigma. Okay, so we're just setting this up. We're going to say we're taking this simple random sample and from this population where we know the mean and standard deviation for that population. If our sample size is greater than 30, then the sample mean has an approximately normal distribution, 2, a mean equal to the population mean. So that's the notation for the mean of the sample, which we would say would be also equal to the mean of the population. And 3, the standard deviation for the sample would be, so this, right, standard deviation of the sample would be the standard deviation of the population divided by the square root of n. Okay. So I mentioned earlier this idea about, our samples are almost never going to be perfectly normal, right? They're not going to be perfectly symmetric. They're not going to be perfectly bell-shaped. But if our sample size is large enough, we can then assume that it is approximately normal and thus use all of the things that relate to approximately normal that we've talked about. Finding area under the curve, finding z-scores, things like that. And then additionally, we can find the mean and standard deviation for our samples or estimate those using these formulas here. Now, why greater than 30? Honestly, that's kind of an arbitrary number. I'll tell you, I don't know exactly why it's 30. My best guess is that it's just through a lot of trial and situations of just realizing, it seems like every time our sample size is greater than 30, this all seems to work out. If you have a data set that is a little bit more skewed, has an outlier, things like that, and you want to be able to apply a normal distribution, you would need a large sample size. Okay, so the larger your sample size, the more it compensates for skew and things like that. If your data is already kind of normal, then thinking population, then a smaller sample size is okay. If I kind of generally know that the population is already generally normal as a data set, maybe I don't even need 30. Maybe 20 or 25 would be a large enough sample size to be able to apply normal distribution characteristics. Okay. All right. So let's do some examples with this then. So again, from that example that we did, example 7 was the adult women in the United States. So it says from example 7, the distribution of women's heights, again, mean of 65.5, standard deviation of 2.5. What is the probability that from a simple random sample of women, the sample mean height is greater than 66 inches? Okay. So in this case now, we're not taking an individual from the population, right? We're taking a sample of 100 women, finding their average height, and determining, how often would we find the average greater than 66. So this is not doing exactly what we did before. This is not value minus mean divided by standard deviation. We are now going to apply the mean and standard deviations that we just talked about here. Okay, so z is now x bar minus the mean of the population divided by the standard error, the mean of the sample, or the standard deviation of the sample. And again, this being sigma divided by the square root of n. So it's going to feel a lot like what we did before, with just a slight variation, especially in that denominator. But in context of the problem, it's actually very different from what we did before. So we're taking 66, that's the value, minus 65.5, divided by 2.5, divided by the square root of 100, because that's our sample size. Okay. That gives us, if we just want to simplify it a little bit, the top is 0.5, the bottom is 0.25, and that gives us a z-score of 2. Right. So already thinking about what that means, right? So 2 standard deviations away is 95% if we think of it from both sides. Now, in this case, we're only really looking to one side. So we should be looking for a value that's around 2.5%, give or take. So we've got the value. And if we go to the table, so again, kind of thinking about the picture here, right? We've got same idea. We've got the 65.5 and the 2.5. So this is 65.5. We want to know the probability that the average of these 100 women would be 66 or greater. Going to the table, and again, I won't go there to show you. You should be able to find this on your own. We would find that the value is 0.9772. But again, that's to the left. We want to the right. So the probability that the average is greater than or equal to 66 is 1 minus that, or 0.0228. So again, what that means is if I were to sample 100 women in the United States, I would expect about 2.3% of the time that the average height of those women is greater than 66, assuming that the average height is actually 65 and a half. If you think about this, what's happening here is this denominator is particularly important, and specifically the sample size, because as that sample size gets smaller, the overall denominator gets bigger, and therefore my z-score would get smaller, and a smaller z-score is going to create, in this case, a larger percentage, right? So the idea is that as the sample size gets larger and larger, we would expect a much smaller percentage because we would expect far fewer anomalies. In this case, if 66 is not 65 and a half, it's not the mean of all women in the United States. So as that sample size gets larger and larger, I'm expecting that mean to get closer and closer, the mean of my sample to get closer and closer to 65.5. Okay. So, all right, let's talk then about central limit theorem for proportions. So when we talk about proportions, we're now talking about, instead of values, we're talking about like percentages or proportions of data. So population proportion, we are going to denote that symbolically with just P. And then sample proportion, we are going to denote that with what we call P hat, just P with a hat over it. Little upside down V. And it's read P hat. Okay. Whether we're talking about values or proportions, we can talk about a lot of the same things that we've been talking about. So a lot of the stuff that we've been talking about for values will also apply here as we now push into this idea of proportions. So P hat would also have a sampling distribution. It's going to have a mean, a standard deviation, et cetera, et cetera, et cetera. So this central limit theorem for P often called large counts, has a similar implication as it did for central limit theorem for values. In this case, though, it's a little bit different. We're going to say this. We're going to say let P hat be the sample proportion for a sample size of n and a population proportion P. The population proportion P. Okay. If n times P is greater than or equal to 10, and n times 1 minus P is also greater than or equal to 10, Then, again, like the other central limit theorem, we can make some assumptions here. We can assume that p hat is approximately normal. P hat is approximately normal. The mean of p hat, like it is before, is going to be the same as the population proportion. And then thirdly, the standard deviation of p hat is the square root of p times 1 minus p all over n. So as you're looking at that, you should be able to see a lot of the correlations between the two ideas. So when we're dealing with values, again, when the sample size is greater than 30, we can assume that it's approximately normal. The mean of the sample is the same as the mean of the population. And then we had kind of that different standard deviation for the mean, which had this idea of dividing by n, which you also see here. Okay, so a lot of parallels between those two different ideas. The big difference here is obviously instead of looking at sample size, a sample size greater than 30, what we want to make sure of is that the proportion in the two different camps. So again, think of P as kind of like a proportion of whatever it is, and 1 minus P is the opposite. So P and 1 minus P make up the entire population. We want to make sure, or sample size, I should say. We want to make sure that that those two camps are both greater than or equal to 10. All right, let's take a look at an example to clarify some of these points. So it says 58% of smartphone users in the United States own an Apple iPhone. If a random sample of 50 Americans is taken, what is the probability that fewer than 50% own an iPhone? All right, so first thing we want to do here is we do want to check for central limit theorem. I'm just going to abbreviate that CLT. We need to make sure that, again, that for both of those groups, that they are greater than or equal to 10. So we're going to take 50, that's our sample size, times 0.58, that is the proportion of Americans who own a smartphone, or excuse me, an iPhone specifically. And that is going to be 29, which is clearly greater than or equal to 10. And then likewise, 50 times 0.42, 1 minus 0.58, is 21, which is also greater than or equal to 10. So CLT checks. So we can go ahead and continue here. So again, first of all, just for mean and standard deviation, mean again of the sample proportion is the proportion, which is 0.58. And then the standard deviation of the sample is, again, square root of p times 1 minus p all over n. And in this case, that gives us 0.07. Now, again, remember what we're looking for is if I were to take a sample of 50 people, what is the probability that fewer than 50% would own an iPhone? Okay, so we need to find Z here. And Z is done just the same way that we would do this if this was not a proportion. So we're going to take P hat minus P, so value minus proportion, divided by the standard deviation. So in this case, we're going to take 0.5 or 0.50 minus 0.58 all over 0.07. And that gives us a z-score of negative 1.14. And then again, just going right to the table, just like we've been doing before, nothing new here. Or, you can do the same thing. You can do use Excel for this as well, or some other technology. We would get 0.1271. So again, what that means is assuming that 58% of Americans do own an iPhone, if I take a random sample of 50 Americans, the probability that fewer than 50% of that sample would own an iPhone is about 12.7%. Okay. We are going to finish up this lesson with what's called basically talking about how we can apply the normal distribution to a binomial distribution. So remember, we've talked previously about a binomial distribution. A binomial distribution is one where you have only two outcomes, where you have independent trials, the number of trials is fixed, and each trial has the same probability of occurring. Okay, so you've got those four criteria that need to be met. Another key factor about the binomial distribution is that it is a discrete distribution. So it's one where the outcomes can be basically counted. We're looking at how many heads would I get, how many sixes would I get, things like that. Normal distribution, remember, is continuous. So one of the keys here is how do you take something that is discrete and apply it to a continuous distribution? All right, so we're going to talk about that right now. So let's start with just kind of how we make this transition. So we are going to let x be a binomial random variable. So x is a random, or I should say a binomial random variable. So binomial random variable with n trials and success probability p. And success probability p. Okay, so then again, talking about mean and standard deviation. So the mean here specifically is mean of x, right? Though it is the mean of the average of the outcomes. And in this case, we can find that by just taking the number of trials times p. And then standard deviation, which we'll abbreviate sigma x, is the square root of n times p times 1 minus p. All right, so again, just relating kind of the same information that we've been seeing previously. How do we find mean? How do we find standard deviation? Using a normal approximation for a binomial distribution. Now, remember, I mentioned that one of the things that we have to overcome is transitioning from a discrete situation to a continuous situation. All right, and I'm going to actually write this down so that we can just kind of have this in front of us. But it's so the idea here is that because binomial distributions, I'm just going to abbreviate that, are discrete. I cannot spell that. Let's try that again. CRETE. Basically, we have to correct for that, right? So I'm going to just say it this way. We correct for continuity by basically we're including a half step. So by including a half step, and I'll show we'll do an example. I'll show what I mean by this. Not halfway, half step to our endpoints or to the endpoints. Okay, so I'm not really going to explain this right now, but you've got it here kind of in writing, so you can kind of refer back to it. But let's go right into an example. This will actually be our last example for this lesson. And I'm going to use the lesson to kind of explain, especially that last part about what I mean by correcting for continuity. All right, so a coin is flipped 100 times. We're going to go back to our old trusty coin flipping examples. And we're going to use the normal curve to find the probability of getting between 40 and 60 heads, okay? All right, so we could do this using a binomial distribution, but again, where possible, we actually prefer to use normal distributions over binomial. And so in this case, we're going to talk then about, well, how does that work? So first of all, in order to be binomial, we would have to obviously check those four conditions. So we're flipping a coin. Are there only two outcomes? Yes. Are the trials independent? Do we have a fixed number of trials? And does each trial have the same probability? And all four of those would check in this case. So then the next question is, okay, so it's binomial. Can I now apply a normal distribution? And the way that we would do that or check for that is through CLT. And so CLT, again, just says, yes, we can if n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. So the probability here of success is 0.5. So if I take 100 trials times 0.5, I get 50. And the probability of failure, or 1 minus p, is also 0.5. That will also be 50. So clearly, both of these greater than or equal to 10. So CLT checks. which means that yes, I am able to use a normal distribution in lieu of a binomial distribution. All right, so let's see how this works then. We're going to start the same way we did with the previous example. We're going to find the mean and standard deviation, and that's found the same way. So the mean is n times p, which we just found using CLT. That's going to be 50. And then the standard deviation is the square root of n times p times 1 minus p, which is the square root of 50 times 0.5 times 0.5. And that gives us 5. Okay, so mean of 50, standard deviation of 5. Now, again, what we're doing here is we're trying to really find area. We're trying to find area between 40 and 60 on a normal curve. So let me draw this out, because that'll also help explain that idea of correcting. All right, so we've got a mean of 50. Right, we've got n 55, and we want to find the area between 40 and 60. All right, so we're finding this. So I had mentioned earlier that when we do a normal distribution, we're finding area under the curve for a normal distribution, that whether or not I include the boundary point doesn't matter. In other words, normal distribution does not distinguish between those two things. It does not distinguish between greater than and greater than or equal to. So whether I include 60 or not, it doesn't matter. It's going to be the same value for area under the curve. However, now because we're dealing with a discrete distribution, and in particular one where the values are all whole numbers, I can only get whole number of heads. I have to keep in mind then, or make sure that I include 40 and 60 and that those are actually part of the calculation of area. So basically the idea is if you think about the picture here, this graph, right, I'd have 61, 62, 63, 64, 39, 38, 37, right? It's just a number line is really all it is. So what I'm going to do is I'm going to instead come to a half step greater than 60 and a half step less than 40. So instead of going from 40 to 60, I'm going to set my endpoints at 60.5 and at 39.5. And that way I guarantee that I'm including 40 and 60 as part of the actual area in this problem. So we now proceed just like we would before to find the area. I'm going to find the z-score, use technology or table, whatever you want to use, find the areas for each of them for 39.5 and 60.5, and then subtract them to get our final answer. So for the first case, for our upper endpoint of 60.5, that's our value minus the mean divided by the standard deviation. That gives a z-value of 2.1. And then for the second one, same idea. We take the value of 39.5 minus the mean divided by standard deviation, and that gives us negative 2.1. We should not be surprised that those values are just simply opposite values of each other because we are symmetric from the mean, right? We're 11.5 units one direction, we're 11.5 units the other direction. So 39.5 and 60.5 are both the same number of standard deviations from the mean, just in opposite directions. Okay, so then we go to the table. I go in or use technology. And for the first one, the area would be 0.9821. For the second one, it would be 0.0179. And so our final answer here, the probability of being between 40 and 60, is just going to be 0.9821 minus 0.0179, which is 0.9642. So that's our answer. So if I flip a coin 100 times, I would expect about 96.4% of the time to get heads 40 to 60 times. So flipping the coin 100 times, right, number of heads being between 40 and 60 out of those 100 would occur, I would expect, about 96.4% of the time. All right, well, that is it for this lesson. Thanks for hanging in there. I know it was a bit of a longer one, and I look forward to seeing you in the next one.